presentations yesterday. Honestly, I sat on the evening and worked on my presentation to come up to this level. So I hope it paid off. And I will do my best to give you some interesting insights also in this topic, which is today recycling methods for secondary plastics. So for the presentation itself, I will turn my video off again so that I can focus really on the content. And then I will start. Maybe for starting, for those who might not have been here yesterday, short introduction. My name is Lucyshyn. I'm Associate Professor for Polymer Processing at the Institute of Polymer Processing, which is part of the Department of Polymer Engineering and Science at Montana University at Leoben in Austria. And I will then start with my presentation. Just a moment. Okay, then let's go ahead. So the content of today's lecture will be first a short introduction, some kind of introduction, some figures and facts about plastic waste in Europe and the world. Also some words about what to do with the waste, what options do we have. Then also the kind of starting point of motivation for recycling, why should we recycle? And then going into more technical tasks about recycling technologies. Structured in that way, there will be a focus on mechanical recycling, and then also a few words to other recycling routes. And then finally, maybe an attempt to answer the question of which recycling path is the right one, although I can already say now there is no real answer to that, no easy answer to that. And then summarize briefly the content. So in the introduction, I would like to start with some figures, some key data of the plastics industry. So thanks to Plastics Europe, it's always a great source of information that we can take, and I've taken that from there. So the plastic industry in Europe gives direct employment to 1.5 million of people, so a lot of people employed in this branch. There are close to 60,000 companies in this field, creating a turnover of more than 350 billion euros and has a trade balance of 17 billion euros. So it is a quite big industry. It contributes to public finances by taxes and so on, about 30 billion euros, and it's a multiplier effect of 2.4 times the GDP, almost 3 times in jobs. And it's an industry that ranks 7th in Europe in industrial value added contribution. And regarding recycling, so over 8.4 million tons have been collected, plastic waste have been collected and recycled inside and outside the EU. So we need to have a look also at the great numbers about plastic production in the world. So worldwide in 2017, we reached about 350 million tons of plastics produced. Not even all plastics there, not the fibers are not included in these numbers here. And Europe contributes with about 64 million tons. So having a look at where the production is happening. So the global player, the big production sites are in Asia. So China, Japan, rest of Asia, so they contribute to half of all the worldwide production. And also Europe and US, there's a quite significant contribution, each about 20%. If we're looking at where do we use the plastics, so we have the big three, the packaging, the building and construction and automotive, where packaging is clearly the favorite or the champion, with counting almost 40% share of all the plastic goes into packaging, and 20% in building and about 10% in automotive, and then the rest is distributed over some other applications. Then looking into different plastics, that's not it's quite clear that we have the polyolefins quite on top, because that's also packaging, it's consistent. So PP, all the variations of polyethylene are there in high numbers. Then PVC, polyurethane are basically coming from this building and construction side. PET also contributes to packaging. So basically that's what we expect if we see that packaging and building and construction are the main players, and these are the polymers used in these fields that is also very consistent. Looking at standard plastics, where are they used? Where are they going to? We see the polypropylene is a very big share. Also all the polyethylene, different types of it, so LD, HD and so on. So once again, the polyolefins are really a very, very big group. So it also in general makes sense to have a look to what can we do about these polyolefins recycling. So maybe it's nice to have solutions for other polymers, which are also existing, but of course, it would be nice to have really good solution for those big parts of polymers. This is also a nice graph showing the distribution of the different polymers here on this axis in different sectors, and the sizes of those squares are indicating the importance or the number of the materials. And you can clearly see once again packaging. Here we have the biggest cubes, the biggest squares, and here again concentrating here in the polyolefins, so polyethylene, polypropylene, but also here PET is quite prominent here. In building and construction, we have different polymers which are most dominant here. The PVC, of course, for pipes and windows, and also polyurethane is quite big, and also polyethylene for all those films that are used. So basically, what do we do with the waste? It's also an interesting question. So we heard about this also in yesterday's lecture, so it's a kind of repetition and revision of this. So we have life service of plastic products, which can be very short in packaging, especially up to 50 years. We heard that yesterday already. And after life is over, service life is over, it is becoming waste. And then we have two options. Non-collected waste, of course, this is not what we want. So it's just littering or going somewhere. And then plastic becoming waste, which can be collected waste. And here in the collection of waste, we have also some options. We can go for recycling. We can go for energy recovery, which is currently in Europe the biggest share. And still there is a lot of landfill happening. What is quite interesting to have some historical view back in comparison of plastics and paper. So in 1980, both of them were 100% linear. So classic, produce, then consume it, and then it's waste. And at that time, plastics had a very good reputation, or like an inherent circularity promise in it, because it's thermoplastic, meaning it's a promise we can remelt it, reshape it, we reuse it. So that's a good promise, and we see what came out. And paper at that time had a very bad image, so it was really just single-used and a lot of littering, destroying nature, reducing oxygen in the atmosphere. So it was not that really a good material. And interesting how it developed until now. So if we have a look at the same materials in 2017, we see that plastics only achieved around 9% of circularity, and the growth of plastics was based basically on linear expansion. And nowadays, really, we have a problem with a very bad image of packaging, and also in the population, also in the society. So it's really a lot of single-use, littering, destroying nature, CO2 in atmosphere. So the image is very bad. That's also something we're fighting. And I really believe that's also one of the reasons that we are fighting with our student numbers and the beginners. So we have really a significant reduction of beginners in the previous years. And I'm really convinced that it's also related to the very bad perception of plastics in the society. And on the other hand, we have paper, and they developed really nicely. So currently around 70% circularity, and the growth was based really on increased circularity. Of course, there are also some issues, so it's not perfect, but certainly it's currently one of the most accepted materials for recycling. So everyone is collecting paper. It's rather easy to collect it and also to recycle it. So that's basically where we should also aim at. Thanks for this slide. That comes from Jugend. But it's really nice to show which options do we have for waste. So coming from the top to the bottom. So the top is most desirable option, and then the bottom is the least desirable option. So basically, the two green ones are before it becomes to waste. We already have some options. So the first option, of course, would be reduce. So if we can avoid waste or avoid having material in the product, because we have other solutions which are maybe more intelligent and use less material, and this would be, of course, the first choice. Reuse is also a good option. So if, for example, we can use bottles again, clean it and use it again, it's also a good idea. And then the other options below are, once it goes to waste, we have those options also in descending order of preference. So first of all, we should try to recycle it if there is an option, if it's possible. Then the next best choice is, if recycling is not an option, go for energy recovery with different possibilities. And really the very last option is landfill. So if we can avoid landfill, it would be the best. Okay, we know all this in different views and different graphs. We've seen that, but once again, just to show the options again. So typically we have this life cycle of starting with some feedstock, maybe fossil-based or bio-based, or even then feedstock or recycling-based. We're doing the plastic production, then we get a product manufacturing and goes to the consumer. There it is used, and then we have the various options after use. So the first one is really acting immediately after this and goes back to the user, to the consumer, which means the reuse and the repair options, which are certainly the most preferred one if it's possible. Then it goes to various options regarding the recycling or the use of the material. One is energy recovery, which means basically we are losing the material, but at least we gain some energy, which also is something good. And then we have the possibilities of mechanical recycling and chemical recycling. Mechanical recycling more or less bridging this feedstock part and bypassing it and substituting original feedstock and going into plastic production or directly into product manufacturing. And chemical recycling basically creates new feedstock based on recycled waste. We see some impressive development, so it's going on. There is happening something. So from 2006 to 2016, we see a development of recycling, energy recovery, and landfill. So landfill has decreased quite a lot. This number looks impressive, but of course, if you're starting from rather low numbers, you can always achieve a high increase. So a relative increase is always easy if you start from a low level. But still, it's going on and it's going in the right direction, but still there's a lot to do. Regarding post-consumer waste in Europe, also based on numbers from Plastics Europe. So currently we have like 40% of the post-consumer waste, plastic post-consumer waste is going into energy recovery, about 30% into recycling, and about 27% still in landfill. What is interesting, if we have a look at different EU countries and different parts of recycling methods, so the green one is recycling, what we want, blue one is energy recovery, is the next best solution, and red one is landfill, which we don't want at all. Then, of course, there was this ban on landfill in some countries in 2016. Unfortunately, the hope was that this would shift from landfill to recycling, but that obviously did not really happen, but basically all the landfill was shifted to energy recovery. So there is still a lot to be done in this field so that we can shift from energy recovery really to material recycling. Also some interesting figures regarding packaging recycling rates in Europe. So there are the green countries are, no, the dark green countries are the good students that do their job best, more than 45% of recycling, and other countries are not that good. What was interesting for me and also a little bit surprising, so from my own perception, I was thinking that we in Austria have a very good recycling rate. I have to admit it was not that, so the numbers tell us a different story. So also here, maybe there has to be done something about that. There is also a mismanagement of waste. So something of the material is going, specifically also a big problem, going into the oceans. And there was one quite interesting study, was published recent or some time ago, showing that 95% of the plastic, which is polluting the world's oceans, pours in from just 10 rivers. So it's not like it's coming in from everywhere and then we have hardly any chance to control that. But that would give us maybe a chance to directly act here on these hotspots. There are some really impressive, in the negative sense, impressive numbers. So about 8 million tons of plastic per year are found in the ocean, which is really, it's one truckload per minute, which is put into the ocean. And there is an estimation that there might be more plastic than fish estimated for the year 2050. So that's certainly a scenario that we don't want to have. Looking at some pictures, so once again, those 10 rivers carry by far the most plastic into the sea, based on this study. And they really evaluated a lot of rivers worldwide, and it turned out that only 10 of them are really relevant. And these are 8 Asian rivers and 2 non-Asian in Africa. So looking at this, that most of it comes from 10 rivers, this ocean cleanup, which is a good initiative, and it is necessary to get rid of what is in the ocean already. It's a little bit absurd because we have a huge ocean and we start to clean up there. I'm not sure if it's, maybe we have a better chance to start on those 10 rivers and have a better effect. But yeah, I'm not an expert in this. It's just my personal perception of this topic. So what is then the motivation for recycling? I mean, it's quite clear. It's one point is also promotion. So in the meanwhile, the attitude of the consumer has changed. So the consumer, I think, is in the meanwhile ready for, yeah, really doing something good for the environment, and being sustainable is a motivation for a consumer to buy something, even if it might be even a little bit more expensive. Okay, this promotion text is in German, I'll translate it. So it's about the kitchen front of IKEA. So what they say, it's like, imagine that your kitchen exists of recycled plastic bottles and recycled wood. And that's the case with our new Kangsbecker kitchen fronts. They have been produced from 99.9% of sustainable materials. And with the purchase of these kitchen fronts, you're contributing to the protection of the environment, and you can take modern sustainability to your home. Sounds really great, and I think consumers are looking at this already. So if it's really 99.9% sustainable materials, then it's good. If it's just greenwashing, of course, we don't want that. So if it's only for promotional purposes, and maybe there it's not completely correct, then it's not good. But if it's really seriously done, then I think it's a good thing that you can do promotion with it, and the consumer is ready to really buy it on this decision. So it's not about, is it cheap? It's not about only how does it look like, but it's also about, can I do something for the environment? Another example to motivate consumers to collect something and to do it is, there was an initiative of DM, which is a big drugstore chain, and they are doing advertising to collect the bottles of the Fa product, which is shampoo bottles, and they were doing promotion that if you as a consumer collect those bottles, and they will be recycled into slides for children, which is very emotional. So that's for the consumer, like, I do something really good, I enable children to laugh, do something good, and therefore it's a motivation that I don't throw it just to the normal waste, but really go to the yellow bag or to the other possibilities. Another example, also showing promotion so that you do something good, is this cooperation that was done, a joint recycling project of Stabilo, Coca-Cola, and Interzero, that waste caps, screw caps, were turned into highlighters. And another example that's also good, if you have some examples showing that it's possible, that's also maybe a starting point for other products, that they see, okay, it is possible, you can do that. And one of those examples is this Trodot Printy. Basically it's an office printer. This was an outcome of a project we were in. The project was called Rec to Tech Part, meaning recycling to technical parts. So it's not about packaging, but really about technical polymers. And in that case, it was about polyoxymethylene. And about this office printer, it was about upcycling of this post-consumer recycled plastic and also post-industrial recycled plastics. And this print is sold now, so it's really, you can buy it, and it's promising that it's using up to 65% of recycling material. Up to the limitation is, if you're buying it in black or dark gray, then it's 65%. If you want to have lighter colors, then you have to reduce the amount of recycling. We had this topic yesterday about the colors. Once it's mixed color waste, then you can only go for dark colors in your product. In this project also, we learned that what we heard yesterday in Kim's presentation, it really was, we had to change our approach regarding the material selection. So typical, the simple procedure is, you have an existing material which you are using, you have specifications of this material, and then the easy way for the producer, the safe way is, okay, if I can get the recycled material with exactly the same specifications or better, then I will use the material. But this is maybe the wrong approach, because just comparing the materials is not what we want. The procedure needs to be, the recycled material does not always need to be equal to the original material, but it has just to fulfill the product requirements, which was possible in that case. So in the end, the material, the recycling material, did not meet all the specifications of the initial material. So the data were not the same. In some points, they were not as good as the original material, but still for the product, it was easily sufficient. So why not use it? So If you're only comparing materials and say, okay, well, this value is not sufficient, then we don't use it, and you don't try out if you can make a product out of it, that's really, you have to change your mindset towards product and not towards comparing simply materials. So once again, summarizing the motivation for recycling, on the one hand, of course, can be price and costs. Currently not the best motivation, as the oil price is down and the virgin material is maybe even cheaper than recycling material. But this also might change if there's a higher cost on oil. The biggest impact, of course, comes from standards, directives, and laws. So that's currently, when it's not a motivation, basically you have to do it. Of course, motivation can be that you want to do something for resource efficiency and CO2, so you save material, you save also in this case costs maybe. And also marketing is in the meanwhile also some motivation. So you can do something if you can say, or you have kind of green brand of your material or your product, this kind of attracts consumers in the meanwhile. So it's in the meanwhile, it's a buying or argument for consumers. So why are we doing recycling once again? So of course we want to reduce the petroleum consumption and CO2 generation, stop landfilling, stop polluting human resources. These figures, some figures were pointed out by Roland Bomberger yesterday already. So the proportion of plastics in the waste is only 15 weight%, but more than 50 volume%. So it's really a volume problem. So it's taking a huge volume. We have to do something about this. And another problem is that 40% of all plastic products have a lifetime smaller than 1 year, and some even very short. And another figure, more than 1 million plastic bottles are sold every minute, but fewer than half of them are recycled. So after this quite lengthy introduction, I would now go to more technical topics now, really going into recycling technologies. So basically, we have different ways to recycle materials. So we are starting from what we get from maybe what we heard in the last presentation yesterday of Stephen de Meester. So they are doing a lot of stuff in separating, cleaning and everything, and then we get some material. And which options do we have there? On one hand, we can use it for material recycling, and on the other hand, we have the option of thermal recovery. Thermal recovery is quite obvious what that means. That we are incinerating the material, and what we get from it is heat, or also we can produce electricity from that. On the material side, we can distinguish between mechanical recycling and chemical recycling. Mechanical recycling, we can either produce regranulate or regenerate. So regranulate would be you just do nothing with the material. You take the recycling material and produce pellets and don't do anything about it. And regenerate would be that you are kind of modifying it and then upcycling it to enhance the property profile. And on the other hand, you could maybe even directly go to a product. So really to use the material and directly produce a product out of it. In chemical recycling, there are typically two paths, going towards monomers and also going towards production of gas and oil. In my lecture today, I'm focusing on mechanical recycling due to 3 reasons, basically. One reason is that there's a limited amount of time for this lecture. Second reason is there will be a more extensive lecture on chemical recycling in the afternoon by one of our ESRs, micro teaching. And third, honestly, I'm not a chemist, so that's not my main field of expertise, so I'm more at home here. So now let's go into mechanical recycling, what it's about. Regeneration of recyclates, I already mentioned that. So why do we need regeneration? Where is the problem? Why do we need that? And the problem is that polymers coming from waste have a history, and typically not the best history. So you have to do something about it. What are the reasons? What is this history coming from? What is happening to the polymer? So one reason is, on the one hand, also that the properties of polymers are really, in the meanwhile, tailor-made and optimized to a very high degree. So the polymers which we are using for some purposes are really perfect or optimized products already. That means that in order to achieve desired properties, several additives and stabilizer systems have been added to the base polymer to achieve those optimized properties. The problem is that those additives are kind of consumed when they're on the one hand processed, but also during their application. So they're added for some purpose to avoid some like external influences or to prevent some problems with external influences. But during the avoidance, they're kind of consumed, and so that they are missing then in the new product properties. So that means that the material properties are changing during processing, during the use. And here we have to talk about this topic of aging. So that's a big topic related to recycling. It's aging. What is aging? Aging is basically the total of both chemical and physical changes resulting in changed mechanical properties, and based on that also in a reduction of the applicability of these materials. We can distinguish between the kind of internal and external aging effects, which I would like to explain now. So internal aging effect means the following. So it's really inside the material. It's coming not from the outside, but from the inside. That can be thermodynamic instabilities within the material, which are mostly affected by heat. So heat is typically accelerating such processes. Some examples are, for example, an incomplete polycondensation. So you have some potential of additional polycondensation happening in the material if you introduce some heat. Might be unstable crystallization states. So there might be going on something in this direction. Might be immiscibility of polymers and plasticizers. So they are forming agglomerates within the material, which are typically starting points for cracking, for example. Internal stresses may be introduced by these instabilities due to inhomogeneous densities or molecular orientations. So that's also coming from the inside. It's already there and happening inside the material. On the other hand, we can talk about so-called external aging. So that's influences coming from the environment. So it's based chemical or physical influences from the environment, which means that typically material surface is very often in contact with oxygen and moisture. And there are typically reactions with oxygen, and they are quite often dominant processes. So oxidation processes are a real problem for polymers. Some examples, so weather in general, so temperature change, UV light and so on, rain and so on. Ionizing radiation could be an issue, heat, chemicals, biological media, which are in contact with the material. So a lot of external influences coming on polymers and change their properties. In terms of aging, so that one distinction would be internal and external aging. Another viewpoint could be that you're distinguishing between chemical and physical aging. So in general, we have material changes which are caused by aging, and there you can see on the one hand some kind of chemical aging, and on the other hand some physical aging. Chemical aging typically results in internal crack formation and some kind of notch effect which you have then. And in the physical aging, we might have change of the crystalline structure, we have increase of crystallinity maybe, we have relaxation processes going on. So all together, both together, we are ending up in quite an explosive cocktail of different bad influences, and then bang, we get fracture of the material. So this all acting together, and it causes that the material will fail, or the product might fail easier or earlier than expected. So we have to think about, we have to understand these aging mechanisms, and then we have to understand how we what we can do about that. Let's start first with some content or some information on chemical aging. So what is chemical aging? Basically, it's all processes which are causing a change in the following material properties. So it's something that is changing the chemical composition or the molecular structure or the molecular weight. And important to know, chemical aging is typically irreversible. So if some chemical aging happens, this is kind of not reversible. Some examples here are oxidation, degradation, hydrolysis, post-condensation, post-polymerization. And that's due to the fact that the weak points of the polymers are their macromolecular architecture and some weak bonding forces in some points. And those changes can be classified into three groups. So one can be the change of the molecular architecture. So for example, a reduction of molecular weight or the change of its distribution, or also some cross-linking and branching happening. Another group could be the forming of functional chemically active groups, which are doing something unwanted. And also some splitting off of low molecular weight components, like depolymerization or splitting off of side groups. These changes can have a dramatic effect on mechanical properties on the one hand, but also color changes and nasty odors can result from those chemical aging processes. Also, in general, the optical appearance might change, so they have quite some effect on the product properties and the material properties. Just an example, so the reduction of molecular weight also significantly affects, on the one hand, the mechanical, but also the rheologic properties. This is the famous Mark-Howing equation, which is a relation between the rheology, so the viscosity of a material related to the molecular weight, and with a very high power of 3.4 of the exponent. So that means a small change in the molecular weight results also already in a very big change in the rheology, which then again causes trouble in the processing. If we have a look at physical aging, they are different. So they are changing the morphology, the molecular orientation, the component concentration, the external shape or surface appearance, or also some generally measurable physical properties. And I mean, that's the good thing about physical aging. These processes are in principle reversible. So if you're changing the conditions, then maybe those things can be reversed. Some examples which are happening: relaxation in material, so like creeping of the material under load, post-crystallization, which is happening, phase separation of different components, additives, migration of plasticizers to the surface, agglomerations, like for example, blooming of additives on the surface, so some like spots or some unwanted surface defects happening. And these physical aging effects are often combined with changes of the physical structure and dimensions. And also there are stresses created inside the material, which then once again result in the crack formation and fractures. There is also a change of, if you're changing the morphology of the material, then this has an effect on the water and oxygen diffusion behavior due to like changes in crystallinity or orientation. This affects this diffusion behavior, and this might have some synergetic effect with chemical aging. So changing the morphology is basically a physical process, but this may also have an effect then on acceleration of chemical aging if oxygen and water can diffuse through the material. One big topic here is the topic of the influence of temperature on aging of polymers. So, of course, we know temperature has an accelerating effect on both chemical and physical reactions. So we know the exponential effect according to Arrhenius. So typical is this typical values. We know that with an increase of 10 degrees, we have double speed of some reaction. There are three cases. I can distinguish between pure thermal degradation, so only heat acting, might be chain scission, so reduction, so the molecular chains are cut apart and we get a reduction of molecular weight. It could be depolymerization, so creation of monomers and separation of side groups for weak bondings might happen. Then also cross-linking can happen at rather low temperatures already, so this can happen. And it's also kind of degradation, so in that case it's not, the size of the molecules is not reduced, but the properties will change if you're cross-linking material. Then we can have thermo-oxidative degradation, so it's thermal degradation in the presence of oxygen, and also thermomechanical degradation, so if you also have some mechanical loads on the material combined with thermal load, then this also increases the aging. So what is happening during processing or reprocessing? So we're at processing, we have the highest temperature for the material, so in use, in application, typically, of course, the temperatures are not that high, but in processing, we have to go to those high temperatures to be able to melt and shape them. And aging, therefore, is also really strongly connected to the processing step. And as those chemical and physical structures influenced by processing conditions. So even if we have only mainly chemical aging in processing, so not physical aging, due to the fact that the processing has an influence on the structure, this also influences the physical aging later on in the use. So mainly we have chemical aging. So what we have in processing, we have elevated temperatures plus oxygen, which are really the fiercest enemies of polymers. So if you have both of them, that's really tough for the polymers to survive. So fortunately, physical aging is typically not happening during processing. So there is not typically weather around the machine and UV light on the material inside the machine, but still the process has an influence on the structure, on the physical structure, on the morphology, which furthermore has some subsequent influence on the physical aging processes. So what can we do about aging? So what are our options to avoid these aging effects? The key is using stabilization or in general additivation. So we add some additional components to the material and try to avoid those bad effects of aging. Why? There is a loss of properties due to the processing and aging. We learned that already. And these are just two examples, sorry, partly in German, but I think should be possible to explain. So turn to the left example. What we see here is from a polypropylene. We have drawn here the MFR, which is the melt flow rate, indicating high MFR means high flowability, which is related to lower molecular weight. So if the MFR increases, then we know that the molecular weight has decreased, so the chain length has been decreased over time. So having a look how this is changing over time in use. We have some virgin material here, which is not changing a lot over time, so there is no reason to change. There is not much happening. But if we have recyclate, which would be the first one, which has not been subjected to oxidation a lot, we already start at a higher level of MFR. So some degradation has happened already. The molecular weight has decreased and the MFR increased. But still, there's not much oxidation, so it's increasing with time, but not that much. But if you have very strongly oxidized material, then you see that it very quickly the MFR goes up. Another diagram in that case for a polyethylene, it's a carbonyl index, which indicates the amount of oxidation which has happened to the material. We have one material which just has been produced. So it's the first virgin material which has been produced. And then you see after a certain time, there will be some oxidation happening. This index is going up. If we are doing reproduction, so maybe house internal, you would put some of the material again into the production machine. We start again at a higher level already, and it's slightly steeper also. And if we go for recycling, then we start at even a higher level. So there has been already some oxidized material from the start, and then it increases also a little bit faster. What does that mean? Also to show what happens during reprocessing, if we are processing material multiple times. On the left-hand side, we see on one hand, again, the melt flow rate is this curve, which is increasing with increasing processing step. So that's the virgin material, then we're doing some processing and again processing the same material. And then we see that the MFR is going up. Once again, that means that the material is degrading and the molecular weight is decreasing. At the same time, and this is just a flow property, but in fact what is more important is then also regarding the application properties, which is the impact strength, which is a very important parameter, and it goes dramatically down. So that means even in the first few steps, it's typically going down. This is an example for a PBT. The other example is a PVC, and here we see the time until yellowing, which means also some kind of degradation effect, which you see that the material becomes more kind of a yellow color. And also here we are seeing various processing steps and how it goes down with increasing processing steps. There is less time required until the material starts to become yellow. And that it's an indication of this oxidation processes going on. So what can we do? We have quite a big inventory of different tools that we can use to add to the material to get the desired properties. So we have to add some suitable additives that can be, on the one hand, polymeric additives that can be in principle also just a mixture of virgin material together with recyclate. So if we are not able to use 100% recyclate because the properties are too bad, then we can make a mixture of virgin material and add some recyclate, and we can see how far we can go, how big the amount of recyclate can be. What is typically done is adding of modifiers. One of the most frequently used is so-called impact modifiers to raise the level of impact strength again. Compatibilizers have been mentioned yesterday also in Kim's presentation. So if you have different phases of materials, they're tending to agglomerate, and to avoid these agglomerations, which are always starting points for cracks, you can use compatibilizers so that you have a more homogeneous distribution of the two phases in one material. What else you can do is also to add some reinforcements. So if the material itself is not strong enough, you can add fibers, or glass fibers, cellulose fibers, You can add some other fillers, talcum, so mineral fillers typically, talcum, wollastonite, calcium carbonate, or also wood flour. And you can also add some so-called functional additives like pigments for coloring, processing aids, some lubrication aids for processing, rheology modifiers, and then various types of stabilizers. Some stabilizers are really made just for processing so that the material survives the processing step. Some are maybe for long-term heat resistance or also light influence, so UV light. And also reactive molecules we can add to increase the molecular weight, these so-called chain extenders, which are working in some materials. So we add those stabilizers and additives anyway also in our previous product. So in the virgin material, these are already present, but typically they have to be replaced in recycling materials because they're basically getting lost. So typically we have to put the same amount into the recycling material as it was in the original material, but most times even more because also the original material has lost some of its properties. Just an example again. So we have here the impact strength drawn against the time. And you see there's a mixture of PP and EPDM. And we have the unstabilized material that after a certain time, the impact strength goes down. So in use. And if you stabilize it with a certain amount of stabilizers, you can see you have some effect. And if you increase the amount of stabilizers, the effect is even bigger in that case. So that means you also need to find out, we have to find a compromise. You don't want to add 50% of stabilizer, of course. On one hand, it's expensive. On the other hand, it still also changes some other properties of the material. So you will have to find the sweet spot of not adding too much of stabilizers, but still getting desired properties. Regarding functional additives, just one slide, a few words, those so-called chain extenders. So basically for polyethylene terephthalate, this is something that is done already. There is a polyfunctional compound which can react with the carboxylate group of PET, and that can use to increase the molecular weight. So it basically can grow the chain of the PET to increase its length and then increase the molecular weight again and increase the properties. The reaction temperature of this is typically in the range of 250 to 330 degrees C. So that's how it might look like. There's a PET with some carboxylate group, and then you have some reactive material which is able to react with that and then start some kind of additional extension of the chain, which results then in better properties. So now I've talked a lot about we're adding this and that to the polymer, but how do we get all of this stuff into the polymer? That's the next question. That's the more technical part again. And that's the answer is compounding. So I have to apologize. I missed that yesterday in the processing lecture. It was, of course, it's one important processing method, but yesterday I was focusing mostly on really final products and not so much on this intermediate step. But in that case, we're doing compounding, as it is called. What is compounders? Compounders are also extruders, but in that case, they're so-called co-rotating twin screw extruders. And what that means is they're basically mixers. The other extruders, the single screw extruders, which I talked about yesterday, are basically trimmed and optimized for output rate and productivity, but they are not that good in mixing. And opposite to that, compounders are not that good in output rate and productivity. So if you want to have a huge amount of pipe produced per hour, that's not the best choice, but they're very good in mixing. How do they look like? The principle looks like the same. We have a hopper, we have a barrel with heater bands outside, and then we have two screws. So from the side view, you only see one. From the top view, you have two screws that we call them twin screw extruders. And we also have a distinction between so-called co-rotating and counter-rotating system. Co-rotating means that the two shafts are rotating in the same direction. And also the geometry of those two screws is in such a way that there is a possibility of material exchange between the two screws, which basically results in a good mixing effect. What you can see here, we have quite a variety of different elements here in the screw, which we can also play with. So that's like a set of yeah, for toys where you can exchange as you like. So you have kneading effect, kneading elements where you have you apply a lot of shear to the material. You have some conveying. You can also add some mixing elements to get some more mixing effect. So that's then a lot of experimental trial and error to configure your screw in a way that it serves your requirements. We have different zones here in this extruder. So first we have, coming from the hopper, some base material, solid conveying, So it's still we have pellets. Then here the plasticizing happens. And then typically, depending on the material, you can either add, you can mix already in advance some materials and put it together and then put it in here. Or especially for powders, it's sometimes useful to add the powder directly to the melt and not to the solid state. So here we have some additive addition here. We can add some powders to the melt. Then here these powders will be dispersed. So we will have some mixing elements here. Then there's some kind of homogenization zone. And we also have the possibility to degas. So if we have some volatile components that could even be water vapor, for example, it has to be taken out of the material, or some other volatile components which we do not want to have in our product, then this can be done here by applying some amount of vacuum, which really sucks the volatile components out of the viscose melt. And then finally we have some melt conveying, and then in the end, which I did not draw here, is we have a die, and the die is basically kind of filaments, and these filaments are cut into pieces and we end up in pellets. So the product of a compounding process is not a real product, it's a pre-product, it's the pellets, which we are then using on the conventional processing machines. So just to show you how it looks like, a short movie, always better than explaining it. Oops, sorry. Get some sound, of course, some nice explanation also.
From the feeding of the raw material to the extruder, all the way to the downstream peripheral equipment, Coperion is your specialist for the implementation of turnkey compounding plants. The heart of each system is the ZSK MC18 twin screw extruder. Here, the two co-rotating screw shafts pick up the feed material, pellets, powder, or other products in solid form. The material is melted and formed into a homogeneous compounded mass in the downstream processing zones.
What is not shown here in this example is that you can also add, have the possibility to add liquid components to the melt. So it's not only, you don't only need to have solid particles, but also you can add liquid additives to the melt. And the main purpose is really to create a homogeneous mixture of all these components, and in the end create pellets which can then be used on a conventional processing machine. And then finally, a few words to other recycling routes. So chemical recycling, as I mentioned, I'm not the real expert here, but still some keywords. So of course, the idea of chemical recycling is that if you have a very heterogeneous and strongly contaminated plastics and blends, you cannot really do mechanical recycling, because all our processing and also all our property profiles depend strongly on the purity of the materials. But fact, of course, is we've seen that yesterday impressively, that we don't get this nice material which we would like to have. So we also have to find solutions for that. And this could be a solution for those heterogeneous material. So what is basically done is the macromolecules are broken down to petrochemical base substances. And there are different possibilities, gasification, so basically oxidation under oxygen deficiency, creating synthesis gas, CO or hydrogen, cracking is a fission process to produce gasoline, fuel oil, or liquid gas, hydrogenation, so it's reaction with hydrogen, coal liquefaction, and to produce fuels. Another topic is the topic of thermal recovery. You can either use, you can just incinerate it and use the heat, but you can also use the material as a substitute fuel in other processes, in other industrial processes. One example is the cement industry. So in the cement industry, you need to heat up the material. So you need some fuel to create this heat. And one possibility is then, in order, instead of using fossil-based fuel, you can replace some of this fuel by just using this plastic waste. And this is just aiding as a resource for creating this heat, which is required for this industrial process. Another example is waste incinerating plant in general. So waste incinerating means you're burning your waste, but burning means you need some fuel to produce this burning. And of course, plastics is a good fuel for that. But you have to be careful about it. So that's my information at least. So if colleagues from waste management are listening, maybe they know more about that. So you have to be careful. If you have too much of plastic waste in it, then it could cause some reduction of the throughput due to the high fuel values. So that the fuel value is too high even and creates too much heat. So that maybe you have to limit the amount of plastics in the incineration plant to 5%. To make sure that there is not excessive heat generated, which might reduce your throughput of your plant. So that's the part of substitute fuel. So instead of using another fossil fuel to create this heat, which is required for the process, we can use this the plastic to create this heat. And on the other hand, it's really incinerated with the purpose of generating thermal energy, which can then be used for heating households, for example. So, or also you can produce electricity with heat. So these are the two options there. I mean, it's not a bad idea, basically, because if you compare the fuel value, which is stored in the materials, you can see that crude oil has a value of 42 megajoule per kilogram. Coal is compared to that even worse. Petrol is a little bit higher, and domestic gas is also in this range. And you can see that even the polyolefins have even higher fuel values than the base material, because it's more pure. You have a lot of carbon in it, which can burn pretty well. So that means really they have a very good value of fuel. So that means it in some kind it makes sense. You first produce a part or a product which is then used, possibly as long as possible. Maybe you find a way to recycle it, and then sometime maybe the degradation is so bad that you cannot use it anymore. So the use as a fuel is still a good option then, to get out of this fuel instead of just depositing it and wasting this amount of fuel of energy which is stored in the material. Which leads then in the end to this question of which recycling path then is the right one, which should we choose? Of course, this cannot be answered in a correct way. You have to consider various factors here. So one factor is we have to think about process-oriented thinking, which is necessary to get an answer in that. So it's not enough to only look at the recycling at the end of the process. You also have to think about the synthesis process, the production process, the product in use. All of these components have to be considered to get an answer of what end of life scenario could be possible. The waste stream is of course a big factor. So you heard that yesterday. We have post-consumer waste, we have post-industrial waste. It can be clean. I mean, clean is an optimistic word here. It's rather clean, or it can be heavily contaminated. We can have rather homogeneous material streams, which is possible in some way for polyolefins or also PET and PVC. There is a chance to get more or less kind of homogeneous material streams. And there, of course, we can have some very heterogeneous material streams. We was mentioned already. Here we can even distinguish between maybe separable. So if we have a chance to separate it, then we have a chance again to go for mechanical recycling. If it's not separable at all, because they are maybe glued together or welded together, we have two component parts or whatever, then maybe chemical recycling or thermal recycling might be an option. Or it's also one option. This material can be milled down to powders and can maybe also used as a filler. So instead of using a virgin mineral filler, maybe we can achieve similar effects which we want to achieve with those fillers with those materials which we cannot do anything about it anymore. We can at least try to use them as a filler. That's also one option. Of course, this has to be evaluated if this makes sense in terms of ecological aspects, in terms of properties aspects, but still it's one option you can also think of. Of course, there's a big factor of economy. So basically the price of the virgin materials is a very important factor. And also the cost structure, how far you will go with the material. This is like the oil price. Numbers are not quite current, but still, of course, the price for raw material for polymers is strongly related to the oil price. And then, of course, if the virgin material price is even lower than recycling material, then why should we use recycling material as a producer? So it's just more expensive, and there is obviously, in terms of economical viewpoint, there is not a benefit of using recycling material with all the problems you carry along with the recycling material, and then you have not even an economical advantage. So that's also a big problem. So basically, oil has to be more expensive and then recycling becomes more attractive. So the evaluation of the best recycling technology really strongly then depends on the degree of contamination. If we have monofraction or multifraction, so of course monofraction would be desired, it's more easy to recycle. In general, sustainability, so if we have a huge process we have to follow to get to the final recyclate, the question is if this is really still sustainable. So it's not just about saving material, but also the whole process chain has to be looked at, and if this is a very energy intensive process and a lot of steps, then this is not automatically that it has to be sustainable. So you always have to look at these sustainability aspects. Of course, if we can wish something, then the preferred route would be mechanical recycling, because then we can use the material, we can use it several times, but reality shows us that it's not always easy to achieve, or it's in most cases not easy to achieve that. According to my opinion, chemical recycling is of course possible, but maybe not yet as economical as we would wish to have it, and also there are some other issues. The thermal recycling is economical, so it's easy to burn it, it's not big effort, but ecologically it's only positive on the energy category. So you gain energy from that, but in terms of other aspects like CO2 and so on, it's of course not the best choice. Okay, so that brings me already to the end of this presentation. So briefly summarizing, so still in general, polymers are great materials with a high potential for circular economy. So it's there, but there are quite some challenges there. One, of course, is to make waste accessible to produce raw materials by recycling. That's what we discussed or we heard yesterday a lot. So consumer has to discard it in some way and we have to get it back to our cycle. We need a lot of process thinking. So it's not only looking in one aspect, but really this global thinking which is required and which is very nicely represented here in this C-PlaNeT project, which we really, I think we really need this approach. So single solutions will not, give us much progress. We also need to think about this recycling friendly design, which was also shown very nicely yesterday in Kim's presentation. We need customer orientation. That's really what that means. It has to be convenient for the customer to do collecting, otherwise he will not do it. And also there is, of course, a good possibility to regulate by legislators, but still the customer has to do it. So it's both sides have to be involved in this. And once again, the final conclusion, still preferred route, we have to work on this and to go in this direction should be mechanical recycling if it's overall sustainable. I want to thank also colleagues of mine, Dr. Martin Spörk and Matthias Quatschnik, who did a great job in helping preparing these slides, and I'm ready now for your questions. Thank you for your attention.
Thanks a lot, Thomas, for your great presentation. I see in the chat a few questions popping up. So Avi is first wondering, how does compounding affect future recycling? And as a follow-up question, I didn't understand what is the difference between regranulation and regeneration. Okay, let's start with the second one. It's easier. So regranulation is just you take the material as it is, but still it has a shape that maybe if you have some flakes or something like that, you cannot use flakes in a conventional single screw extruder. So in a single screw extruder, you need quite defined shapes of your pellets, otherwise it cannot be conveyed. But if you get some recycled material which is not in this shape, you first have to bring it into this shape by compounding. So you basically just melt it and you pump it through a die producing this filament, and then it's cut into pieces and we have the pellets in the desired shape. But you don't do anything to the material, you just melt it and give it a more regular shape of the pellets. Regenerating means you're doing something with the material by adding additives. So that's the base difference between granulating, which is a very simple process, and regeneration, which is mostly done. And the first question, I mean, compounding, you have a lot of possibilities in doing compounding. So you have a variety of additives you can add. And you can also play a lot with the process conditions within compounding to achieve different property profiles. So it's really which kind of elements you're using, how much mixing you're doing, how much shearing you're applying to the material. So you can influence a lot the final product properties or the pellet properties by changing the process settings of your compounder. So I think it's, in terms of mechanical recycling, there is quite some good perspective of using compounding to
kind of tailor-made or tailor your pellets again to desired properties.
Okay, thank you, Professor. And then a second question from Dixit. How will recycling become attractive to industries with so fluctuating crude oil prices? Do you have any comments on that?
That's a good question. When the oil price affects not only recycling, but also our complete mobility topic. So as long as fuel is so cheap, there is not much motivation to change to other like battery electric vehicles or something. So it's the same topic there. So maybe we need to have a realistic price on oil with all its resulting bad effects on environment, because if we can avoid some bad effects on environment, or otherwise using oil or consuming oil results in some bad effects on environment, and that also causes some costs, but this is difficult to grasp. So if we are able to like assign the real costs to this material, then maybe oil has to be more expensive, and then it goes in the right direction. It also, for example, bio-based materials also become more attractive. It's all going in the same direction. So if crude oil becomes more expensive, recycling becomes more interesting, bio-based materials become more interesting, mobility becomes, so non-fossil mobility becomes more interesting. But it's difficult to say, because oil price is something that is happening. I'm honest, I have no real answer about this question, how to make it more attractive if it's so strong depending on the oil price.
I think you hit some important points there. We have a next one from Yi Liu. It's a question about the slide where you compare the virgin low density polyethylene, polypropylenes with those materials comprising recycled recyclates. So what is the aging condition for them?
I just have to think. I must admit, I don't know exactly what the aging of these, what the specific aging conditions were in this specific case. It was just more an example, a general example of showing that something is happening in aging. But I must admit, for this specific graphs, I don't know exactly. I took that from some literature. I don't know exactly what were the concrete conditions there.
But the references were on the slide, so it can be checked. And okay, perfect. Let's head over to the next question from Professor Den Doelder. Can regenerative compounding be fed with flakes to avoid an additional first pelletization step, which indeed implies cost?
Yes, that's the advantage of this compounder. So, but flakes have to be defined. What is flakes? So flakes can't be like 10 centimeters in diameter or something. So they have to be cut down to a certain extent, but the shape can be irregular. So if you have really flakes, which are like, if you shred a plate, then you will have flat flakes which are quite sharp edges and so on. This could not be used in a conventional injection molding machine or in a conventional extruder, but this can be used in a compounder. So a compounder is able to convey such kind of material. So that can save the first step of producing those granulates. So we don't first need to produce pellets and then go for regenerative compounding, but in this regenerative compounding, you can also use those flakes to a certain extent. If they are too big and too irregular, then there are also some limitations. It's also strongly depending on the size of your compounder. If the bigger the compounder is, the bigger also the flakes can be, because then also the screws are bigger, and then you have more possibility to put in bigger particles.
Okay, thank you. Then there's also an important comment by Namrata, who indeed says that the ocean cleanup also has these interceptors in place now in certain rivers, which try to capture there's some plastics. Okay, then perhaps the next one from Mubarak. What are the challenges of balancing consumer requirements with governmental regional regulations?
I think that it's kind of good that there are some legal governmental requirements and regulations for important topics, because if you only ask the consumer, I think the consumer is not the right person to decide on these really important topics. So For the consumer, of course, it's more convenient to not to separate the material. For the consumer, it's more convenient to have a cheaper material. But if in general for our society, it's good that we have to do something about recycling, and I think we have to go this way about regulations. And then I think also the consumer is, we are adapting to our situation. Same as a student, if you have the professor is very strict and you have to learn more, then you will learn more. If you don't have to learn more, you don't do it. So we're ready to adapt if the regulations are there, all counting on volunteering and doing it voluntarily. This does not work in many aspects. We see that. So same for Corona measures. If you say everybody is done voluntarily, then we have a lot of people not wearing a mask. So you have to do some, for important topic, I think these regulations are good. And for that, I'm really happy also that we have EU doing something in this direction.
Thank you. I think next one is also important. So Cleo wonders, how many times can we recycle a material? Or how good can we still recycle already recycled plastic? So it's secondary recycling.
Yeah, that's also a topic which is, I think you have to answer this question individually for each material, for each product. So it depends on the one hand on the product requirements. So if the product requirements are not that high, then you can maybe do some more reprocessing, and also on the material. So if you have materials which are very sensitive to thermal degradation, then it's more difficult to process it several times. This has to be found out kind of a little bit on trial and error, and then kind of database has to be created on this, I would say. So it's not easy to answer for each. It's really an individual decision, and you can have a look at this by doing experiments, by really reprocessing the same material several times, and each time you're doing some characterization of the material and then getting some insight into the behavior. But there is no general answer to this. Sorry, it's a little bit of a political answer, but it's true. It's hard to answer in a direct way.
Next one is also an important one, in my opinion. So Morteza wonders, how can petrochemical companies, which produce quite a lot of plastics, contribute to this circular economy? Do you have any input, idea on that?
I think one topic is, of course, if there is a chance to create materials or create a higher variety of properties with one material. So this going towards only one material solution is very a good point. So if we manage to have one material and maybe different properties by different morphologies, for example, which is basically one of the topics here also in C-PlaNeT, this would be, I think, a good approach. But this requires really some designing of new polymers, or not new polymers, but modifying existing polymers that they can have different properties, which finally fulfill the requirements. That would be one option what I would think of, but maybe this can be commented also by material suppliers, which are also present.
Yes, indeed. There are some material suppliers present in the audience. If they would want to comment, feel free to turn on the microphone.
All right, this is Sylvie from Dow. Can you hear me?
Yes.
We can. Hello.
I just started to type an answer, but I can verbalize it here. So there are different ways in which petrochemical companies can participate in the circular economy, we believe. For the first part, and the most obvious one, I'd like to refer to one of the first options on using recycled material that Professor Lucyshyn was mentioning. So one of the approaches to actually enable the use of recycled materials that are sometimes a little bit contaminated or degraded is actually to use additives, right? Antioxidant, but also impact modifiers, for example, which are then often virgin impact modifiers that are produced by the petrochemical industry. The same story goes for compatibilizers. And then another route is one that we're looking at today is actually to use virgin, very high performing molecules, so very well designed polyolefins, and mix these with a a stream of recycled material in order to compensate for the degradation of the polymers. And so that's one of the more obvious reasons or obvious ways in which the petrochemical industry participates in this in the circular economy, let's say.
Thanks a lot for your contribution. Any other input on that?
Yeah, I can add a few things. This is Jaap, if I take that perspective.
Please go ahead, Jaap, and then after Jaap, we can have Inge.
Sure. Let's not forget the chemical recycling or the feedstock recycling, which is also an obvious route. So Professor Lucyshyn has been sketching the pros and cons. Obviously, if you go back to the monomers or the building blocks, then the classical raw material polymerization companies are fully into the game of repolymerizing it back. So that's one thing. And then the design for recyclability, all polyolefin that Dixit is going to work on in this project is obviously, just to echo what Thomas was saying there, a non-trivial but very interesting path. So there's multiple options, non-exclusive, but it's of high interest.
Dixit will also be presenting this afternoon on his topic. And then I give the word to Ms. Daams from ExxonMobil.
Hi, you can call me Inge, thank you.
Inge.
Hi, so I'm Inge Daams from ExxonMobil. So obviously we also work on this topic. Two things that we're working on, for example, and these are some of the things we're working on, is really understanding how we can include recycle in new structures. We see recycle as a new type of virgin material, and we have to, well, as a new type of raw material. Let me tell it like that. And the idea is to compensate for performance loss with virgin materials. So the better we can make the virgin materials, in order to compensate for some of the specific property losses that were mentioned by the professor in the talk we just had, the better, of course. So that's one of the things that we're working on. And then also design for recycling is something that we're heavily working on. We used to see a lot of let's say laminates in the market. So these are multi-layer structures with many different materials in there. The question is, how can we shift these materials more and more into, or these applications more and more into monomaterials? So that's something else we're working on.
Okay, thank you.
Thank you for the input. Is there anyone else who wants to comment on that one, or we head on to the next question?
I would also like to make some comment.
Of course, go ahead.
Yeah, we are, I mean, as actually the representative of Dow mentioned that similarly, we are also making some sort of especially polymers that could help when it comes to recycling polymers, meaning that you could improve the impact strength or some other properties of the recyclates by adding some of our products, like the quill grade. This is something that we could do from the virgin polymer side. On the other hand, we also have very ambitious targets of increasing the volume of recycled plastic solutions to 350,000 tons per year by 2025. So basically, we have acquired 2 recycling plants already, which has a capacity about 50,000 tons and 40,000 tons per year, respectively. And in the meantime, we are also working on building up a new chemical recycling plant in the next few years' time to further expand our production capacity. And in the meantime, we are also investing on the possibility of building chemical recycling plant. And this is still in the kind of initial phase. But I think as Brias, we believe that we have to complete the recycle kind of the entire chain of possibilities, including chemical recycling, mechanical recycling, and even looking into possibilities of solvent recycling. So basically, you need to have different possibilities. Of course, I mean, each of the solutions, as the professor mentioned, has its pros and cons. But in the end, you might need to have to work on all of the solutions to have like really comprehensive and final solution to this critical problem of circular economy. So that's coming from my side.
Thanks a lot for your input.
Thank you.
There's still a few minutes if anyone else would want to comment on that one. Otherwise, I will pass on to the last question. So please interrupt me if you'd like. Then we head over to the last question from Namrata. It's again quite a technical question. Could we say that regenerative compounding will result in upgraded recycling?
Well, yes. So upgraded in terms of based on the starting point. So the material we have at the beginning has a lower property profile than the virgin material, and we would like to enhance the properties again to the initial properties. But even it's possible in some time to get better properties than the initial one, depending on the, of course, on the level of the initial one. But that's the basic idea. Regenerative compounding means you enhance the properties of the input material. So it has better properties after this compounding step.
Okay, thanks a lot. Okay, that concludes the morning session of the third training day. So in the afternoon, we start again with open lectures at 1 a.m. So 3 of our ESRs will present their first results or their topic. So it will be ESR 2, 10, and 11 with topics on chemical design for recycling, chemical recycling itself, and also a topic on mechanical recycling of recycled films. So see you again this afternoon, and thanks a lot for joining in this morning.